welcome to this problem walkthrough. Today, we will explore problem number 756, Pyramid Transition Matrix. We'll break down the problem, discuss different approaches, and analyze their efficiencies. Let's get started. In this problem, we are given a string called bottom that represents the bottom row of a pyramid, and a list of triplets called allowed. Each triplet in allowed defines a valid transition for building the pyramid. Specifically, a triplet, A, B, C, means that if two adjacent blocks in one row are A and B, then C can be placed directly above them in the next row. The goal is to determine if it's possible to build the pyramid all the way to the top, or each successive row has one fewer block than the row below it. To clarify the input structure, bottom is a string of length between 1 and 8, containing uppercase English letters from A to Z. The allowed list contains up to 216 triplets, and each triplet is a string of 3 uppercase letters. The output should be a Boolean value, true if it's possible to construct the pyramid, and false otherwise. Let's now explore some examples to better understand how this works. In the first example, the bottom string is BCD, and the allowed triplets are BCG, CDE, G, FFF. Starting with the bottom row BCD, we look at the first pair BC. The triplet BCG tells us that G can be placed above BC. Next, we look at the pair CD, and the triplet CDE tells us that E can be placed above CD. This forms the next row, which is GE. Now, for the pair GE, the triplet GEA allows us to place A above it. At this point, we've successfully built the pyramid with A as the top block, so the output is true for this example. This demonstrates how the pyramid can be constructed step by step using the allowed transitions. Let's look at another example to see a case where the pyramid cannot be completed. In the second example, the bottom string is AABA, and the allowed triplets are AAA, AAB, ABA, ABB, BAC. Starting with the bottom row AABA, we first look at the pair AA. The triplet AAA allows us to place A above it. For the next pair, AB, we have two possible options, A from AAB, or B from ABA. Finally, the pair BA allows us to place C using the triplet BAC. This gives the next row as AAC. However, this row cannot transition to a valid single block at the top using the given triplets. Since there is no way to build the full pyramid, the output for this example is false. This highlights the need to carefully explore all possible transitions to determine if the pyramid can be completed. When solving this problem, there are several constraints and edge cases to consider. First, if the bottom consists of a single block, the pyramid is already complete, and the answer is always true. Next, if no valid transitions exist in the allowed list for any pair of blocks in the bottom, the output should be false. Another important scenario is when there are multiple valid paths for transitioning upward. In such cases, it's necessary to explore all possible paths thoroughly before concluding that the pyramid can't be built. Finally, for larger inputs where the bottom has a length of 8, the problem can become computationally intensive due to the exponential growth and potential transitions. Efficient handling of these cases is critical to ensure the solution works within the constraints. Understanding these edge cases is essential for implementing a robust solution. We begin by considering a brute force approach to solving the pyramid transition matrix problem. The intuition here is to build the pyramid one row at a time, starting from the given bottom string. For each pair of adjacent blocks in the current row, we check the allowed list to find all valid triplets that can form the next row. This process is repeated recursively until we either reach the top of the pyramid, with only one block remaining, or determine that no valid configuration exists. To implement this, the first step is to pre-process the allowed list into a mapping, where pairs of blocks are associated with their possible next blocks. Then, a recursive function is used to generate all possible rows and check if the pyramid can be built. While simple in concept, the brute force approach is computationally expensive. Its time complexity is exponential, as the number of possible configurations grows rapidly with the height of the pyramid. Additionally, it has a space complexity of O, h, to account for the recursion stack, where h is the pyramid's height. While the brute force approach is straightforward to implement, it suffers from severe inefficiency due to the exponential growth in the number of possible configurations. To address this, we can use an optimized approach that incorporates memoization. The idea here is to avoid redundant computations by caching intermediate results. This way, when the same subproblem arises, such as determining whether a specific row configuration can lead to a valid pyramid, we can simply reuse the cached result instead of recalculating it. The steps are similar to the brute force method. Start by pre-processing the allowed list into a mapping, then use a recursive function to build the pyramid. However, this time, we add a cache to store results for each row configuration we encounter. If the pyramid can be successfully built, we return true, otherwise, we return false. This optimization significantly reduces the computational overhead. The time complexity improves to approximately n squared asterisk m, where n is the length of the bottom row and m is the average number of valid blocks for each pair. The space complexity increases slightly to n squared to store the memoization table. By introducing memoization, we drastically reduce the computation time compared to brute force, but this comes with a slight increase in implementation complexity. Another possible approach is an iterative method using breadth-first search, or BFS. In this method, we generate all valid row configurations level by level, exploring each possible path using a BFS queue. While this approach ensures that we systematically explore all options, it's less efficient than the recursive approach with memoization, as it requires maintaining the BFS queue in memory. This leads to higher space usage overall. The time complexity is similar to the recursive approach with memoization, but the added memory overhead makes BFS less practical for this problem. Although it's a viable alternative, BFS is generally not chosen due to these trade-offs in efficiency and memory management. The approach we ultimately chose is the optimized recursive solution with memoization. This method strikes a balance between time efficiency and implementation complexity, making it well suited for the pyramid transition matrix problem. By caching intermediate results, we eliminate redundant computations, which significantly improves performance compared to the brute force approach. At the same time, the recursive implementation is easier to read and maintain compared to the BFS alternative. Several key observations make this approach particularly effective. First, the problem can be viewed as a tree of possibilities, where each row depends on the configuration of the row below it. Many of these configurations overlap, leading to repeated subproblems, which memoization helps address. Additionally, pre-processing the allowed list into a map allows for efficient lookups during the construction process. While this approach does require slightly more memory than brute force, its efficiency, simplicity, and scalability make it the best choice for solving this problem. In conclusion, the recursive approach with memoization is the most practical and efficient solution for the pyramid transition matrix problem. It combines the strengths of reduced computational time, scalability to handle larger inputs, and a clear implementation structure. By leveraging memoization, we address the inefficiencies of brute force while avoiding the memory overhead of BFS. This strategy not only ensures that the problem is solved effectively but also provides a framework that is easy to understand and maintain. Overall, this method represents the ideal balance of performance and simplicity, making it a robust solution for this challenging problem. To solve the pyramid transition matrix problem, we start by understanding the input structure. The bottom row of the pyramid is provided as a string, while the allowed combinations of blocks are given as a list of triplets. Each triplet specifies that if two blocks, say at NB, are adjacent, then a third block, C, can be placed above them. Our task is to determine if it's possible to build the pyramid all the way to the top, where the apex is a single block. The first step in the algorithm is to parse this input for efficient processing. Specifically, we pre-process the allowed list into a dictionary called allowed_map. This dictionary groups all valid blocks C for each pair of adjacent blocks, A, B, as keys. By doing so, we enable quick lookup during subsequent steps. For example, for a triplet, A, B, C, we use the first two blocks, A and B, as the key and append C to the list of possible values for that pair. This pre-processing step ensures that future operations on the data are optimized for speed and clarity. After pre-processing the input, the next step is to define the recursive function that will determine if the pyramid can be constructed. This function, can_build, is responsible for verifying whether the pyramid can be built from the current row upwards. The function operates with two cases. The base case checks if the row contains only one block. If so, the pyramid is complete, and we return true. The recursive case handles rows with more than one block. For each pair of adjacent blocks in the current row, we look up all valid blocks that can be placed above the pair using the allowed_map dictionary. These blocks are then combined to form possible next rows. The function uses recursion to evaluate each generated row, checking if the pyramid construction can proceed successfully. To generate the next row, we iterate through the current row, consider all adjacent pairs, and explore all valid blocks for each pair. Backtracking is employed here to explore different combinations of blocks for the next row, ensuring that all potential configurations are tested. If any combination results in a valid pyramid, the algorithm concludes that the pyramid can indeed be built. While implementing the algorithm, we must also account for edge cases that could arise. For example, if the allowed list is empty or fails to cover all adjacent pairs in the bottom row, the pyramid cannot be built, and we return false. Similarly, if no valid triplet exists for a given pair of blocks, the algorithm should terminate early. For larger inputs, optimization becomes crucial. Memoization is applied to cache intermediate results, avoiding redundant computations and significantly improving efficiency. Several key insights emerge from this approach. First, the recursive structure of the problem allows us to focus on building the pyramid one row at a time, reducing complexity. Second, backtracking is essential for exploring all possibilities, as multiple valid blocks may be available for the same pair. Pre-processing the allowed list into the allowed_map dictionary is another critical optimization step, allowing for constant time lookups during recursion. Memoization adds further efficiency by reusing previously computed results. Finally, the base case ensures that the recursion terminates when the pyramid reaches its apex with a single block. Data structures like dictionaries, lists, and sets play a pivotal role in organizing and accessing data quickly. Analyzing the complexity of this algorithm gives us a deeper understanding of its performance. The time complexity is primarily influenced by the number of recursive calls, which depends on the height of the pyramid and the branching factor, the number of valid blocks for each pair. In the worst case, this combination results in exponential growth. However, optimizations like memoization help mitigate this to some extent. The space complexity is determined by two factors: the recursion stack, which is proportional to the height of the pyramid, and the memory used for caching intermediate results. Together, these factors ensure that the algorithm can handle a range of input sizes while maintaining a balance between computational efficiency and memory usage. This analysis highlights the importance of combining recursive structures, backtracking, and caching to tackle complex problems like the pyramid transition matrix effectively. Here, we begin by importing the defaultIct class from the collections module, which will help us manage the mapping for allowed transitions efficiently. Inside the pyramid transition function, the first step is to construct a dictionary called transition_map. This dictionary maps each pair of blocks, represented as A, B, to a list of possible blocks, C, that can be placed on top of this pair. We iterate over the allowed list, processing each triplet and populating the dictionary accordingly. Next, we define a recursive backtracking function called can_build_pyramid. This function will determine if it's possible to construct a valid pyramid starting from the current level of blocks. The base case here is straightforward: if the current _level contains only one block, that means we've successfully built the entire pyramid, so we return true. If not, we need to transition to the next level. To facilitate this, we introduce an inner helper function, construct_next_level, which will handle the process of generating possible next level configurations based on the current level. It works by iterating through pairs of adjacent blocks in the current level. For each pair, if it exists in the transition_map, we retrieve the valid top blocks that can be placed on this pair. This is where the recursive structure of the solution starts to take shape. If the current pair of blocks doesn't exist in the transition_map, we terminate the construction for this path by simply returning. However, when valid blocks are available, we iterate through them and recursively call the construct_next_level function, appending each valid block to the partial_next_level string. This builds up potential configurations for the next level of the pyramid. Once we've processed all pairs in the current level, the fully constructed next_level list is populated with possible configurations. After generating the next level, we then iterate through each configuration in next_level and recursively call the can_build_pyramid function to check if any of these configurations can lead to a valid pyramid. If we find at least one configuration that works, we return true. If none of the configurations lead to a valid pyramid, we return false to backtrack and explore other possibilities. Finally, the recursion is initiated with the given bottom level, and the result of can_build_pyramid, bottom, determines whether the pyramid can be successfully built. This approach ensures we explore all viable paths while efficiently pruning invalid ones, leveraging the recursive depth-first search strategy. Here, we start with the implementation of the pyramid transition logic in Java. The first step is to build a mapping for all allowed transitions, where each pair of characters maps to a list of possible third characters. This is done using a hash map called transition map. For every triplet in the allowed list, we extract the first two characters as the key and the third character as the value. If the key doesn't already exist in the map, we initialize it with a new list and then add the third character to that list. Next, we define a recursive function named canBuildPyramid that will determine if it's possible to build a valid pyramid from the given bottom row. This function handles the core logic of recursively validating each level of the pyramid. If the bottom row reduces to a single block, the pyramid is considered valid, and the function returns true. The recursive function canBuildPyramid continues by generating all possible next levels from the current level. To do this, we use a helper method called constructNextLevel, which builds potential next levels based on the transition map. If at least one of these next levels can eventually form a valid pyramid, the function returns true. Otherwise, it returns false. In the constructNextLevel method, we iterate over the pairs of blocks in the current level. For each pair, we look up the valid blocks that can be placed on top, using the transition map. If no valid blocks are found for a pair, the function exits early, as no valid next level can be constructed. Otherwise, for each valid block, we append it to the partial next level and recursively continue constructing the rest of the level. After each recursive call, we backtrack by removing the last appended block to explore other possibilities. The constructNextLevel method completes by adding the fully constructed next level to the list of possible next levels once the end of the current level is reached. This ensures that all valid combinations of blocks for the next level are generated and stored. This recursive approach continues until either a valid pyramid is formed or all possibilities are exhausted. By combining the transition map, the recursive validation, and the backtracking mechanism, the algorithm systematically explores all potential configurations to determine if a pyramid can be formed from the given starting row and allowed transitions. To solve the pyramid transition matrix problem, we begin by parsing the allowed transitions. Given the list of allowed triplets, we map each pair of blocks, A, B, to the possible third block, C, that can sit above them. For example, the triplet BCG maps B, C to G, CDE maps C, D to E, and so on. This results in a transition map of B, C, G, C, D, E, G, E, A, F, F, F. Once the transition map is ready, we start constructing the pyramid recursively. Beginning with the bottom level, BCD, our goal is to work upwards level by level until we reach the top of the pyramid, which should consist of a single block. Starting with the bottom level BCD, we construct the next level by processing pairs of adjacent blocks. For the first pair, B, C, the transition map gives us G. For the second pair, C, D, the map gives E. Combining these, the possible next level is GE. Now, we recurse using this new level GE. Here, the first and only pair, G, E, maps to A, and this results in a new level A. Since this level consists of a single block, the pyramid is valid. Therefore, the output for this example is true. In the second example, the bottom level is AA, and the allowed triplets are AAB, AAC, CAA, and CCC. Parsing the allowed transitions, we map A to B, C A to A, and C to C. This gives the transition map A, B, C, A, C, C. Starting with the bottom level AA, we construct the next level by examining the pair A. The map provides two possibilities, B, C. This means the next level could be either B or C, and we need to explore both paths. For the first possible next level, B, the pyramid construction halts immediately because there are no transitions in the map that start with B. Similarly, for the second possible next level, C, the pyramid construction also halts because no transitions exist for pairs starting with C. Since neither path leads to a valid pyramid, the output for this example is false. In the third example, the bottom level is XYZ, and the allowed triplets are XYA, YZB, and ZAC. Parsing these transitions, we map X, Y to A, Y, Z to B, and Z, A to C. This results in the transition map X, Y, A, Y, Z, B, Z, A, C. Starting with the bottom level XYZ, we begin constructing the next level. For the first pair in XYZ, X, Y, the transition map gives A. For the second pair, Y, Z, the map gives B. Combining these, the possible next level is AB. Recursing with this new level AB, we process the only pair, A, B. However, the transition map does not contain any valid transitions for A, B, making it impossible to proceed further. As a result, the pyramid construction fails, and the output for this example is false. The time complexity of this solution is primarily influenced by the recursive backtracking process and the generation of possible next levels in the pyramid. To understand this, let's start with the construction of the transition map. Creating the transition map involves iterating through the list of allowed triplets. If there are m triplets in the list, this step requires O(m) time, as each triplet is processed once. Next, we consider the recursive backtracking process. At each level of the pyramid, we calculate all possible combinations of blocks for the next level. If the current level has a length k, there are k1 pairs of adjacent blocks. For each pair, we look up the possible transitions in the map. If B represents the maximum number of possible transitions for any pair, the total combinations for the next level will be proportional to O, B caret, K1. This process continues recursively, with the number of levels in the pyramid being roughly equal to the length of the bottom row, n. Combining these factors, the overall time complexity in the worst case is approximately O, B caret, n1, where B is the branching factor and n is the number of blocks in the bottom row. Now, let's refine the analysis by considering the best, average, and worst case scenarios. In the best case, if a valid pyramid is found early in the backtracking process, the recursion terminates without exploring all possible configurations. This depends heavily on the specific input and allowed transitions. On the other hand, the worst-case scenario occurs when the algorithm exhaustively explores all configurations, resulting in the O, B caret, n1, time complexity we calculated earlier. Shifting our focus to space complexity, there are two main contributors: the storage for the transition map and the memory required for the recursive call stack and next-level combinations. The transition map stores all m triplets from the allowed list, with each triplet requiring O(1) space. Thus, the map takes O(m) space in total. For the recursive calls, the depth of recursion corresponds to the pyramid levels, which is at most O(n). At each level, we store all possible combinations of blocks for the next row, requiring O, B caret, K1, space at level K. In the worst case, this amounts to O, B caret, N1, space for the deepest level. Combining both components, the total space complexity becomes O, M plus B caret, N1. Finally, comparing this solution to a naive brute force approach highlights its efficiency. A naive method would generate all possible pyramids without pruning invalid transitions, leading to an exponential blowup in complexity as it explores every possible configuration for a pyramid of height n. By contrast, this solution leverages the transition map and eliminates invalid paths early, significantly reducing redundant computations. Mathematically, the branching factor B determines how quickly the number of possibilities grows at each level, while the recursion depth is capped at O(n), corresponding to the height of the pyramid. The space complexity combines the linear storage for the transition map with the exponential storage for recursive levels, resulting in O(m plus B caret, n1. Ultimately, the time complexity of O, B caret, n1, and the space complexity of O(m plus B caret, n1 illustrate the challenges of solving this problem through backtracking, while also emphasizing the importance of optimizing transitions and pruning unnecessary paths to improve performance. When tackling this problem, there are several common mistakes to watch out for. First, many overlook the constraints imposed by the allowed list. It's tempting to assume that any triplet could be valid, but only those explicitly listed in allowed should be considered. Ignoring this leads to unnecessary computations and ultimately incorrect results, as the pyramid relies on strict rules for valid transitions. Another mistake is failing to prune the search space when using a brute force approach. If a partial solution is already invalid, continuing to explore it wastes time and increases runtime drastically, especially for larger inputs. Additionally, some forget to handle base cases, such as when the input string has just one character or when the allowed list is empty. These scenarios may seem edge cases, but skipping them can cause runtime errors or produce incorrect outputs. Lastly, the choice of data structure for the allowed triplets matters. Using a list for this purpose is inefficient, as the lookup time is O(n). A set, on the other hand, allows for constant time lookups, making the solution far more efficient, especially when the input size grows. Some additional pitfalls include assuming that all triplets in the allowed list are unique. While this might seem harmless, failing to check for duplicates can lead to redundant computations, wasting both memory and processing time. Shifting to interview-specific insights, this problem is a classic example of recursive backtracking, similar to solving word ladders or Sudoku puzzles. Recognizing when to use recursion, coupled with memoization, is crucial. Memoization, in particular, helps store intermediate results, preventing redundant computations and significantly improving performance. During interviews, it's also important to articulate the trade-offs between brute force approaches and optimized methods. For instance, pruning paths early or leveraging memoization might increase complexity, but the runtime gains are often worth it. Be ready to explain these decisions clearly. Lastly, always test your solution with edge cases, such as when the input string is minimal or when no valid triplets exist in allowed. This demonstrates a thorough and thoughtful problem-solving approach. This problem also has connections to several related problems, which can help in understanding its structure better. For instance, LeetCode 51, the n-queens problem, shares a similar recursive backtracking approach with constraints. LeetCode 37, the Sudoku solver, is another example where valid configurations must adhere to strict rules. Similarly, LeetCode 212, Word Search 2, involves recursive exploration combined with pruning, and LeetCode 139, Word Break, is an example of dynamic programming applied to recursive exploration. Considering alternative approaches, backtracking with pruning is a common method. Here, you build the pyramid layer by layer, discarding invalid paths early on. The trade-off is that while it avoids unnecessary computations, it can still be slow for larger inputs. Dynamic programming offers another option, where results for previously solved subproblems are stored in a bottom-up manner. This approach is generally faster but requires more memory. Lastly, a graph-based approach can be employed by modeling characters as nodes and transitions as edges, which provides a unique perspective but adds implementation complexity. Each method has its pros and cons, and understanding these trade-offs is key to selecting the right approach for a given scenario. Great job making it to the end. To summarize, we explored recursive backtracking for solving the pyramid transition matrix problem and highlighted its key concepts. Remember to practice and apply these techniques to similar problems. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!